really want to focus on in this video is another example where we're using sine or trigonometric functions for sling load calculations. In these first two examples, the first example and this example, we're going to use sine for both of those, but we will be using cosine in subsequent videos. Well, let's go ahead and jump into this one. Very similar, really it's identical to example 1, but there's one major difference. Let's go ahead and read through the problem. And there's no drawing with this problem. You may see a question like this. And again, I keep forgetting my question mark. And not a very good question mark, but it's a question mark. And you may see a problem like this with no drawing. Just it describes the problem to you, and you have to create a diagram from the written description. What is the force applied to each leg of a two-leg sling where the sling angle to the horizontal equals 40 degrees and the mass of the load is 3,750 kilograms? So you've probably already noticed one difference, but let's go ahead and draw out our diagram. Again, I cheat with the computer, but here's what your diagram could look like, something like this. You have each leg of the sling, you have the angle to the horizontal. That's wording that you will see on CSP exam, ASP exam. They'll refer to the angle as the angle to the horizontal or the angle to the vertical. We will have an example where we are looking at angle to the vertical in a subsequent video. Again, draw out your problem like this. The major difference for this problem compared to the other one is that we're in metric units. And the metric unit of force is not pound force, it's the Newton. And force in newtons equals the mass times the acceleration. Mass times acceleration. So we have to do a preliminary calculation to get our mass into newtons. Again, force equals mass times acceleration. Again, acceleration is the acceleration of gravity, which is a constant 9.8 meters per second. Go ahead and plug in our mass, which we have 3,750. Then our 9.8 constant, and there are they're the newtons. This 36,750 newtons is the equivalent of 3,750 kilograms for our purposes, and that's what we're working with, just like we worked with pounds in the previous example. Next step, divide this force by the number of sling legs. We have 2 sling legs. We have 36,750 divided by 2, 18,375. I already had this up here, but I like to double check my math. If I was really being anal, I'd go back and check my math here, but you guys can check it for me. See if I made any mistakes on that one. So we divide force by the number of sling legs. We come up with 18,375. The next step, bisect the rigging triangle, which creates 2 right triangles. 18,375 will be used as a force vector and represent the vertical side of the right triangle. Once we have this information, that's all we need to use sine. We can use the sling angle of 40 degrees and 18,375 representing the opposite, along with the sine function to solve for the sling loading. Again, just like the previous problem, we're solving for h, which will represent the sling loading. Again, sine equals opposite over the hypotenuse. The value for the opposite, 18,375, plug that in. Go ahead and plug in the degrees. So we have sine 40 equals 18,375 divided by h. Now we need to solve for h, and I'm using the shortcut method on this. The previous example to show you the mathematical operation, so you know how I'm coming up with what I'm coming up with, I gave you the long version. This is the short version. The short version is simply taking the 18,375 and sliding it over to the left side of the equal sign and making it the numerator of this fraction, where we have 18,375 divided by the sine of 40. And that's going to give us h once we do these calculations here. Sine of 40, let's go ahead and double check my math here. Sine 40, 0.64. The sine of 40 is 0.64. Okay, now all we need to do is take 18,375 and divide it by 0.64. 28,710.9 newtons is the sling loading on a single leg of this two-leg sling. Again, that's the same loading on both legs. It's not just on this leg. Now, there are situations where the loading could be different on different legs, but we're not. The CSP doesn't go into that, and we're not going to go into it in this class. If you take a full-blown rigging class, you're going to talk about a lot of different variations on these types of problems. But again, if you're taking a real rigging class, you're not going to be using trigonometric functions to solve the problems.